Hello, and welcome to the AQUALIS Sustainable Water Compliance Summit session, Renewing an Urban Neighborhood Through Flood Control Innovations. I am Bob Crossan. I'm the editorial director of the Endeavor Business Media Water Group. To begin, let me explain how you can participate in today's event. First of all, if you have any technical difficulties during today's event, please put your question into the questions window, and our technical experts will help you out. Additionally, we welcome your questions during today's event. We will answer as many as we can at the end of the Q&A session, and that will follow that we will answer as many as we can at the end of the session. So please feel free to send in your questions at any time during this presentation, even at the end or during the middle of it. So to do so, simply type your question into the question window on the side of your screen and hit the submit button. Also, please be aware that today's event is being recorded and you'll be notified via email when the archive is available. At the conclusion of the webinar, you will also receive an email with a link to download your certificate, which can be used to submit for credit with Stormwater University or to serve as a or to serve as one personal development hour for attending today's webinar. Certificates will be sent to attendees who view this session for a minimum of 50 minutes. For those viewing with this session on demand, you'll need to complete and pass a short quiz at the end of the session to receive your certificate link. Now, introducing today's speaker, we have Garrett Johnston. He is National Technical Leader for Stormwater at Freese and Nichols. His experience includes 1D and 2D hydrologic and hydraulic model development and calibration, mapping, condition letter of map revisions, flood mitigation planning and implementation, benefit cost analysis, and grant applications. He regularly teaches HEC-RAS 2D workshops at dam safety and floodplain management conferences and is proficient in the HEC-MS, HMS, and HEC-RAS InfoWorks ICM in FEMA BCA, in ArcGIS Pro, and Python automation. Lots of letters to navigate there on my end. He is a licensed professional engineer, a certified floodplain manager, and certified geographic information systems professional, and he received a master's and bachelor's degree in civil engineering from Texas A&M University. And with that, I will toss it over to Garrett, who can begin today's presentation. Thank you so much, Garrett.
All right, thank you, Bob, and thank you everybody for joining. My name is Garrett Johnston. As Bob said in his introduction, I'm the National Technical Leader for Stormwater for Freese and Nichols. I'm going to be presenting to you today on a case study about renewing an urban neighborhood through flood control innovations. And so I'll go ahead and get started on that here. Before I get into it, just wanted to kind of set the stage with a few key concepts that I'll be covering. The first one is that urban flooding problems can be addressed with nature-based solutions. And I'll be talking about how we applied that in this specific case study. Infrastructure project designs can be both functional and community-centered. They don't necessarily have to be opposed to one another. Community engagement in this case was essential to help us inform and help refine our design approach. And then another thing that's just always good to keep in mind is to expect the unexpected during construction. So just briefly, what I'll be covering today is a case study on Rodney Cook Sr. Park in Atlanta, Georgia, and the design process, the planning and design and construction process that produced the beautiful park you see there in the picture on the right. I'll cover just general background and flooding of this area that prompted the project. I'll cover the planning effort that we went through to phase the combined sewer separation. And then that planning effort was really necessary before we got into the meat of the design, which I'll also cover. And that includes the wet pond you see there, the flood storage, and the green infrastructure elements surrounding the pond. I'll also talk about the construction process, how the project performed after construction, and the lessons learned through that process. So with that, I will jump right into it here. So this image here shows downtown Atlanta, kind of there on the lower right. And then the red area outlines Proctor Sandy Creek Watershed, which is about 23 square miles. It drains a large area of Atlanta. The watershed drains a big chunk of downtown there on the right, and then kind of flows northwest there to Proctor Creek. The upper portion of this watershed is very developed, includes part of downtown. And in that developed area, which is kind of highlighted there in red, I will be zooming into that here in a moment. Most of that area, the natural waterways in that upper portion were enclosed into a combined sewer system long ago when Atlanta was first developed, which presented a lot of the problems that we are trying to address with this project. So this slide kind of zooms in a little bit more. You can see Cook Park there outlined in kind of a lime green color. And that is situated in the middle of Vine City, which is a neighborhood near downtown Atlanta. It had its heyday kind of in the 1950s and 1960s. Was a middle-class neighborhood and was actually the home of Dr. Martin Luther King Jr. In 1968. Over the last 30 years or so, there's been a steep decline in the population. There were repeated flooding issues. This Cook Park area that you see outlined there was or is the low point of the drainage there. And it outfalls to Proctor Creek, which you can kind of see labeled at the upper left of the image. So Proctor Creek down there is not enclosed, but in the area, the Vine City area, all of that, all of the surface, the creek there was enclosed into a combined sewer system. The Vine City area had very low occupancy rates. There were very few acres of planned green space. 41% of households are below the poverty line, 20% are vacant, and there was a high foreclosure rate there as well. And a lot of this kind of stemmed from the flooding risk in this area. So on the next slide, I'll talk a bit about that. This is just yet another view. You can see Cook Park highlighted there in green. And the stream network, or the historic stream network, you can see there in blue. So that's kind of where the kind of natural stream network was before it was enclosed into combined sewer. And so the Cook Park site, you can see that that's kind of where these two tributaries met before they ultimately drained into Upper Proctor Creek. And in that low-lying area, in 2002, there was about 6 feet of flooding. That combined sewer system was about 108 inches in diameter. So it was a pretty sizable system, but it was not enough to convey the flooding in 2002. And so that low point where previous to this project, there were some homes and apartments, they flooded. There was 6 feet of combined sewage flooding. So it was a major event. Lots of people were impacted by that. Over 60 homes were purchased by the city as a result. There was an EPA consent decree for the Upper Proctor Creek watershed. And so the city kind of had this mandate to separate the sewer and storm drain systems from one another, eliminate the sewer overflows, and figure out how to get the flooding under control. And so the city identified Vine City, that area that I showed on the previous slide, as the prime spot for stormwater detention, as a place to kind of hold water and keep it from flooding downstream properties. And because of kind of the history of this site and the civil rights leaders that lived here, and just the historic park that used to be there before everything was enclosed in, there was a real opportunity here for multiple partnerships between the city and the community and like the different departments of the city, like the Watershed department and the Parks department, to cooperate with each other and resolve flooding concerns while also restoring community health. So this is a view of before the 2002 flood event. You can see the outline of the park there and the homes and apartment buildings that were in that area compared to 2017, just before we started this project, where all of those had well, almost all of those properties had been kind of cleared out, acquired by the city, and cleared for this project. You can see, I mean, the impact of this, and just imagine all of the people who lived here and what they had to deal with 6 feet of flooding in their homes. It's pretty substantial. The partnerships that I alluded to before, the City of Atlanta's Department of Watershed Management handled the pond design and construction, combined sewer separation, green infrastructure, and soil remediation. So kind of the civil engineering and consent decree kind of aspects of this project. They also partnered with the Trust for Public Land, who handled the park design and construction. So there's also a park element to this. This isn't just a functional project. This is a community amenity as well. And the Trust for Public Land partnered with the city's Department of Parks and Recreation, as well as the city's Department of Watershed Management. Another partner was the National Monuments Foundation. They designed multiple statues of historical and civil rights leaders that would be kind of scattered throughout the park to commemorate the history of that neighborhood. And then there were other adjacent projects that we needed to coordinate with as well. And that included a green streets project that the Department of Watershed Management was also leading, along with the city's path project, which had to do with establishing a network of trails in the city, and another park project. So there was a lot of different partners and a lot of people who were contributing to this. Really, what I'm going to be focused on for this presentation is what we achieved in with our work with the Department of Watershed Management, with the pond design and everything that went into that. There was a major community engagement element with multiple public meetings, community workshops, online surveys, stakeholder interviews that we did to get an understanding of the public's needs and what they were looking for in a park. So this was a major aspect of the project that unfortunately don't have time to get into here, but there was a lot of feedback and a lot of back and forth with the community to make sure that the park would meet the needs of what they were looking for in the community, and wasn't just going to be, okay, here's a pond, we need to address this flooding issue, but that it would also be something that would provide the neighborhood with an amenity that they had input and feedback and provided direction as to how that part would go. All right, so getting into the specific elements of the park, you can see here in the red outlined area, this is the area that our design was focused on the pond elements, the flood storage, and the green infrastructure. But you'll also see there kind of on the left, there's the Great Lawn, amphitheater, playground, splash pad, sports court. So all of that kind of like more park side, that area was kind of up on higher ground, and that area was led more by the Trust for Public Land and the city's Parks Department, as well as another engineering consultant, while the Department of Watershed Management and what I worked on was kind of more centered here on the right in red. But there was a lot of collaboration between the two. But that red area is really where all of the flood mitigation and green infrastructure was focused. So again, west half focused on park and programming elements. East half here that I'm going to be focused on is the stormwater detention and green infrastructure. So in that area, the project elements that I'll be going over are the kind of the centerpiece, the wet pond. It's about 1 acre, and it has a littoral shelf around it, which is just another way of saying created wetlands. And it also, that wet pond stays wet all the time. But then when a major storm comes through, there's a 100-year flood storage pool that it fills up not only this area on the east side of the park, but it also fills up the west side of the park as well, that Great Lawn area, to provide additional flood storage of up to 30 acre feet during the 100-year storm event. There's also aerating water features, stormwater planters, bioretention areas. There's underground storage for makeup water, A major element here that you can't quite see in this picture, but I'll cover on later slides, is that we had to reroute a combined sewer trunk line that kind of went right through that wet pond area. We rerouted it around the east and north sides of the park there. And then there was other civil engineering work that we did as well for storm drain pipelines, trash racks, sidewalks, workway improvements. But I'll step through all of these as we continue to zoom in here. Before we did all that, we had to look at the phased combined sewer separation. So again, this area was all kind of developed and enclosed. All the drainage went into an enclosed combined sewer system. So all the rainfall that ran off and entered inlets and storm drain lines ultimately wound up in a combined sewer system with sewage as well as this storm runoff. And we needed to plan this park such that our pond would be able to receive just, you don't want the combined sewer to empty into the pond, obviously. That would only be receiving the storm runoff. And so the ultimate project that we're really planning for here is not just with this project, but with future projects, that we want to be able to capture that storm runoff, keep it in a separate system, a new separate system that outfalls into this pond, where that flood runoff can be held back to prevent downstream flooding, while the existing combined sewer would continue to receive, your typical sanitary sewer flows. So this phased combined sewer separation, we used software called InfoWorks ICM. The city provided their model of their combined sewer model, as well as a separation alternative that another consultant had prepared for them. And so we took that and refined the model, revised the hydrology and hydraulics as part of that model. And it took a lot of planning and a lot of thought to settle on a feasible ultimate configuration that we could design the pond around. We needed to decide, okay, in the future, right now we're building this pond, but ultimately we're going to need to extend up these storm drain lines and inlets, and we need to know how big are those pipes going to need to be, which areas are they going to pick up, and which areas are they ultimately going to bring into this pond. So we had a lot of planning effort there to settle on that ultimate configuration. The first phase, the green area that you see here, I'm going to back up one slide. That green area is the area where if a raindrop falls in that area, it's going to ultimately end up in the pond immediately after construction. The purple and the blue areas are areas where those are going to continue to drain to the combined sewer system until such time as the city does a separate project to pick up that area and take it through new pipes into the pond. So that ultimate phase, what we called phase A, captures 73 acres draining to the pond. So we planned out all of the storm drain that needed to capture that. But then these future phases, we would extend storm drain up to capture the Georgia World Congress area there to the east, as well as the Foundry Street area there to the southwest. Adds another 36 acres that we can pick up. And then phase C, the full build out, captures the entire design area. So we would be picking up 150 acres total draining to the pond. And all of this, by the way, has since been constructed. So this was kind of a planning effort that we went through when we were designing just that initial park and pond. But since then, it's been a few years. The city has since designed and constructed storm drain to capture this entire design area. So the first picture you see here, this is a post-construction picture. I'll get into the construction later, but you'll see here when I'm talking about the wet pond, this is what it looks like. So it's a pond that retains water at all times. It improves water quality downstream. This littoral shelf that you see kind of encircling the pond and the little berm that you see out there in the middle of the pond captures trash and large sediment and things that we want to kind of stay on the park site and not continue downstream. So this is really kind of the main water quality treatment aspect of the project. So it provides a functional purpose, but it also just looks nice, provides a community amenity. The littoral shelf around the edge there in addition to improving water quality, it also improves the oxygen content of the water, the habitat for the fish that live in the water, and just improves the aesthetics as well. Water also is recirculated through this at all times. So there's a fountain at the upstream end and a rocky channel. I'll show pictures of that later, but essentially there's always water flowing into this pond. And then at the downstream end, water is pumped, circled up to the upstream end, comes out of a fountain, and drained back down through the wet pond so that we get constant recirculation and aeration of the water. There's also a cistern that we designed that is sized to provide about 20 or 30 days of makeup water in the event that, if it doesn't rain for several weeks and this water kind of starts to evaporate off, we have some makeup water that the city can drain back into the pond without having to use potable water. But I'll circle back to some of these water quality improvements later. Right now, I want to focus on the flood storage, like what happens when it rains and this wet pond water level rises. So, like I showed previously, we've got 150 acres draining to this location. And so when all that water drains to this location, we want to hold back as much of this water as we can to keep it from flooding downstream properties. We had 7 different points of inflow around the pond. And then we had like one very small outlet that I'll show here in a minute, as well as an emergency overflow weir that will engage when the pond truly fills all the way up. So during the 100-year event, provides a safe way for water to exit the pond and flow downstream without flooding any of the neighboring properties. So here's kind of an aerial view. You can see the wet pond there outlined in blue. That's the normal pool elevation. During the 2-year storm, you can see that fills up. So, this is a relatively small storm event, still a pretty major storm event, but, on average would have a 50% chance of occurring in any given year. Fills up that pond to about this yellow outline here. So it would flood kind of like this low-lying park and walkway area. And there's a small outlet down there. It's about like a little 18-inch opening with a little trash rack around it so that water can gradually drain out of that location. And then during larger events like the 25-year storm, it fills up this Great Lawn area over there to the west in green, but is still only draining out through that very small outlet. During the 100-year storm, it fills up, slightly larger area. We go from green there to orange. All that area is underwater during the 100-year event. Excuse me. But during the 100-year, we also have this emergency weir, because at this point, if the water were to get any higher, it would start to flood this low spot of the street next to the project. We don't want that to happen. And so over here on the second circle, I've got an overflow weir. It's about this 80-foot wall that I'll show here in a second, that engages and drains the pond through that secondary outlet. So I'll show that here. You can see that this weir wall, it's an 80-foot wall placed very close to the retaining wall. You kind of squint, you can see that in the distance there's a couple of holes in that wall. Those are some 4x3 boxes. Those, again, engage in the 100-year. Water gets right up over the top of that 80-foot wall, fills this trench on the right, and drains out of those pipes. And as part of that design, bear with me here. As part of that design, we kind of had to really think about how water would get to this outlet point. Our 100-year water level of the pond, that design parameter was very important to prevent flooding of the surrounding streets and properties. And because, just for aesthetic reasons, we wanted to place this 80-foot weir wall very close to that retaining wall. In my engineer brain, I wanted to kind of like push that as far away from the retaining wall as we could, just so that we would provide plenty of room for that water to overtop the weir wall and then go through the holes in the retaining wall and drain out. But just for aesthetic reasons, and because we want the park to be beautiful, we want to have a lot of landscaping there around it. Our landscape architects wanted to push that as close to that retaining wall as possible, and so we had a little bit of a complex design process here to place it as close as we could here, while still making sure that our design elevation, it wouldn't drive up that 100-year water surface elevation too high. So we prepared a 3D model to verify that weir coefficient. And I thought I had a little video of that in here, but that doesn't seem to be working. But I'll just move on to the next slide here. You can see this is another view of the 80-foot weir wall. Just looking at it from the other direction. So the park there on the right side of the screen, this area that you see with the sidewalk and all this landscaping, that area goes underwater during the 25-year event. And then during the 100-year event, water overtops that weir wall and flows out. Okay, so that is a good overview of the flood mitigation function of the park. I'm going to shift gears here and talk now about the green infrastructure elements of the park. Like I talked about earlier, this entire system currently discharges to a combined sewer system today. So you might be thinking, why would we want to treat water quality? Like, why would we want to improve the water quality if we're just going to be dumping that water back into a combined sewage system? And the answer to that is that this is envisioned to be the first of several projects, right? Like we're playing the long game here. We're looking forward to a time at which, the city can move downstream to this next area and continue that combined sewer separation out downstream, ultimately completely separating all of the storm drain from the sanitary sewer. So again, the goal here is to design the project to improve water quality with that future goal in mind of improving water quality with downstream projects as well. So in order to achieve that, we designed several resilient tiers of green infrastructure. So you've got the wet pond that I talked about already, but we've also got stormwater planters at the kind of interface between the roadway and the park itself. We've also got bioretention in a couple locations. We've got the created wetlands around the pond itself. And then I'll talk as well about the rainwater harvesting cistern. The stormwater planters, you see the little design detail here. This is our first tier of treatment. And so all this is curb cuts for the street drainage. So any runoff from the street, instead of going into kind of like a typical grate or like an opening in the curb, it just goes through a curb cut into rows of planters. And this was a custom design that we prepared based on the City of Atlanta standards. The road slopes were a little steep, which made it kind of challenging. So we had these kind of multiple tiers of stormwater planters. As water enters those planters and fills them up during a very large storm event, water can kind of safely overtop those different tiers before ultimately overflowing into the pond. And so you kind of got a picture of the end product here, where you can see the planter next to the road, next to where water can cut through the curb, enter these planters. So in very small events, if you get like an inch of rain, if you get half an inch of rain, it's fully captured by the planters. That's great. And then during larger events, a good chunk of that water is captured by the planters, but at a certain point it becomes too much for the planters, and at that point it just kind of overtops and flows down into the pond where it can be treated there. The bioretention cells that we designed were the second tier of treatment. These are also sometimes called rain gardens, and they work in a similar way as the stormwater planters. They improve water quality before reaching the pond. Water kind of soaks through this engineered soil and into a perforated pipe before it drains into the wet pond. So that's what would happen during your smaller events. Water would just kind of soak into that soil. All of the sediments and anything that might be in the water that you don't want to be in the water would get kind of captured in this bioretention cell, so that the water that flows out of that perforated pipe is a lot cleaner. And here's a picture of what that looks like. This is just immediately after construction, so the greenery hasn't like really fully been established, but you can get the idea there. It provides kind of a small pond area where during small rain events, water that didn't make it into the planters or that didn't soak into the ground in the planters makes it to these bioretention ponds. Gets another chance to soak in, but in an even larger event, it just overtops the side of the bioretention pond and makes its way directly into the wet pond. The created wetlands, or the littoral shelf that I showed earlier, is our third and final tier. It just catches any suspended material in the in the plantings before it enters the pond. And so here's kind of another close-up view of that around the edge of the wet pond. So this is our penultimate tier of water treatment here before it reaches the wet pond. I alluded to this earlier and briefly mentioned it, but the wet pond is kept full when it rains on the 150 acres that drain to it. So that's the way it's intended to work. So if, during small rain events, water makes its way into the wet pond and gradually replenishes it. But if there's a drought, if there's a long period without rain, if that level drops due to evaporation, the city wanted to be able to fill it back up, but didn't really love the idea of using potable water, putting the chlorinated water into this pond where they wanted to have fish, and they wanted to maintain natural rainwater in this pond as much as they designed this rainwater cistern so that they could refill it with that. And what you'll see here that's kind of outlined in a dotted line, that's one of the storm drain outfalls. It's a 48-inch pipe, I believe, drains out through like an arch pipe into the pond. But then to the south you see that other kind of black pipe that reaches out to the south. That is a pipe that we designed to overflow during small rain events, something like a 2-year event or less. And that way, when water comes down through this 48-inch pipe and is refilling, we want it to refill the pond first. But then if there's any additional water, if this pipe is full, we want some of that water to spill off to the south here and refill these concrete boxes that constitute our rainwater cistern. So this little storm drain setup that we designed it in such a way that any overflow from that storm drain would fill the cistern, and it has enough volume to provide about 20 or 30 days worth of backup water. So here's a picture of you can see the arch opening. I've got the red line there that kind of shows you where that storm drain comes out. And then got this little lateral storm drain that then goes and fills this underground cistern that you can't see, but it's kind of under that grassy area there to the right. And that's where we hold our backup water. So at the end of the day, this project provides about 135,000 cubic feet of treatment volume. It removes total suspended solids, about 80% of those. It also removes phosphorus, fecal coliform, and metals. The majority of this treatment is provided by the wet pond itself. So as water enters the pond, the velocity slows down and all of that material can kind of settle out. But the bioretention cells and the stormwater planters also provide a good amount of treatment volume, and that is really helpful for smaller rain events. Your everyday little half an inch of rain type of storms. The other thing I wanted to mention is that this is a retrofit project, right? This is an area that we're working with a space that we have available, and so we're trying to treat as much water quality volume as we can, but ultimately we are constrained on space, and on what we can realistically achieve with what we have available. So the typical target for water quality treatment for like a new development would be about 1.2 inches. So like if you get a 1.2 inch rainfall, you would want to be able to capture and treat all of that with the water quality treatment elements that we have as part of this project. After phase A, so after that initial pond construction, we were treating about 1.5 inches of rainfall from that initial drainage area. And then after the additional storm drain was constructed upstream to get that full 150 acres draining to the pond, at that point we're treating about 2/3 of an inch of the rainfall that falls on that 150 acres, which is honestly pretty good for a retrofit type project. If the city wanted to in the future, they could construct additional green infrastructure upstream in those areas. So, provide additional rain gardens, additional stormwater planters, bioretention, whatever they want to put upstream, they could construct that and provide additional treatment. But for the project that we're talking about today, we provided about treatment of about 2/3 of an inch of rainfall, which again, not bad for a retrofit project. We've got some pictures here of construction. One of the things that really added some time to this project was the soil remediation. And I don't have all the background information on this, but essentially the soil testing early on in this project revealed that there was a lot of soil contamination, lead and whatnot in these soils. I think it had to do with this area being developed as an industrial area many years ago before it developed as a neighborhood. And so for that reason, there had to be a significant soil remediation effort up front as they excavated the soil for this project. We're essentially digging a big hole in the ground to make this this pond, this park, and to provide that detention volume that's so badly needed to mitigate the flood risk. But then what do you do with that soil? You can't just take that contaminated soil and put it someplace else. So there had to be a remediation effort. So that added some time to the project. You can also see there some of the installation of the pipe and the cistern there on the bottom. And then performance. So this is a picture of a storm so let me back up a little bit. Construction took place roughly 2020 to like 2022. And this picture here that you see was during a storm that occurred in September of 2023. They got about 2.6 inches in an hour, which roughly is about a 50-year storm for this area. And you can see here that walkway right there, that little arc, you can kind of see that the handrail there. If I skip forward a couple pictures, that's that main walkway there over the pond. And that was pretty much fully underwater. And so the pond worked as designed. It contained runoff from the upstream areas that normally would have caused substantial flooding. It was all kind of captured and contained in this area. So it is performing as designed. And there have been a few other storms since then. I think, if I remember correctly, I think this is the largest one that they've had since it was constructed. Couple lessons learned, and then I'll start showing off some cool pictures, and we can move on to Q&A. But that remediation effort that I mentioned earlier, soil remediation, took a bit longer than expected, and that added on a few months to the construction time of the project. There was also a clay liner that we installed, like at the pond level where the wet pond was. The reason for that being we didn't want there to be interaction between groundwater and surface water. We wanted to keep those separate, so we had a clay liner. And so the time to excavate all of that soil and install the clay liner was by far what took the longest during construction. There were some right of entry constraints that we had to just do a little redesign in one area. Another issue was that the dewatering system, again, we're digging a big hole in the ground here. That's the purpose of this site, is to capture rainfall. Well, that happens during construction too. So due to the kind of larger than normal amount of rain during construction and the operation of the dewatering system, the construction area that's flooded multiple times during construction, which just caused delays. That's just kind of part of the deal when you're building a project like this. And all of the above increased construction time from the planned 18 months to about 36 months. So the final product here, you can see this was an artistic rendering of the project early on, before we had done any construction whatsoever. And then here is a picture from a drone immediately after construction was completed. So you can see downtown Atlanta there in the distance. You can see the enormous Mercedes-Benz stadium. It looks like a big spaceship. And then the neighborhood surrounding this beautiful park. I did want to mention here, this is a view along Boone Boulevard, which was a roadway project designed by another consultant. It was a master plan trail system that raised the road, which was kind of part of what was needed to prevent flooding. And also they connected their stormwater planter outfalls to our project. So you can kind of see in the distance, you see some stormwater planters. So that is where we captured runoff from their area and connected it to our storm drain outfalls. I think some of them went into the bioretention and some of them just discharged directly into the wet pond. A few other pictures here. You can see here a picture of one of the civil rights leader statues that they put in the park. There are several of these around the park. I think this one is of John Lewis. And then a few other things that were put around the park were just some little informational signs for the public with QR codes and just information on how green infrastructure works. So there was a public education piece of this as well. Excuse me. It's a picture of the bioretention that I showed earlier. Picture of the wet pond. Another view of a trail system surrounding the wet pond. And then this, I don't think I showed a picture of this before, but this is the fountain at the very upstream end, kind of the southeast corner of the park. And so this is where water is pumped from the wet pond back up through this fountain, spills over this area, goes down into the rocky channel, and then goes back into the wet pond. So this area is kind of constantly recirculating. Another view from that general angle. And that is all I have. So I'd be happy to answer any questions that you may have here. I think some of those have been placed in the chat, and
yeah, we've actually got quite a few questions that have come through for you, Garrett. So thanks for the presentation. Yeah, well, I'll kick us off with one, but before we get to that, I saw that there's someone in here that says they're from the city of Winston-Salem and they work with Freese and Nichols on some stormwater projects, so they wanted to give it a little shout out there. So
nice.
thought that'd be a nice thing to call out. But how do you balance the technical flood control requirements with the community's vision for the park? That seems like you got to balance both sides of that equation. I imagine that can be relatively challenging.
So you see, I mean, the picture you see here, I mean, I talked about this a little earlier with the park side kind of being the west side and the more engineering side, the flood control side being on the east side there. So I think early on in the project, there was a little bit of push and pull about like, okay, how are we going to integrate these together? You know, we could just kind of wall it off and say like, okay, this team does their park design over there. We do our flood control design over here, and we don't talk to each other. And you could just kind of wall it off and operate that way. But we really wanted it to be kind of more of an integrated, the city wanted it to be more of an integrated approach. And that I mentioned it earlier as well, that Great Lawn area, big kind of green spot just west of the wet pond is part of the park area that the park team worked on. But we had a lot of coordination with them to make sure that the way that they graded that out provided the volume that we needed on our side, so that it really kind of operates seamlessly as one large pond, even though we didn't have like direct control over that side of the pond. We had to coordinate with them, and that obviously impacted their design of like where they could place the park, where they could, I mean, the playground, the splash pad and whatnot. Yeah, there was a lot of back and forth, a lot of communication that had to occur early on in the project before we got into the nitty-gritty of really designing this.
Yeah. Well, I'm going to combine a couple of questions here because I was looking through and it seems like there's a little bit of a theme here. We had one was like, how is the ongoing maintenance of the green structure elements being handled? There was also, how long has this project been in operation? Have you had any issues with sediment deposition from large flows? Do you include any measures to facilitate cleaning of surfaces after such an event? And then again, how much would a project like this cost? Timeline for completion? After complete, who's responsible to maintain it? So there's this theme of like
Yeah,
maintenance,
maintenance.
and then
Yeah.
yeah, so not just like not just the total project cost, but also the operational elements, and then these maintenance elements that are going to have to,
Mhm.
you're going to have to maintain it after these larger events. So thought I'd kind of bundle all of those together into one and give you an opportunity to kind of like tackle each of those bits individually.
Sure. The total cost of the project was about 40 million, but there were a lot of partners that kind of, I don't have all the information on exactly who paid what piece of that, and there may have also been some grants involved. I'm not sure, but about 40 million in construction total for this whole thing. The As far as the maintenance goes, there we had a detailed operation and maintenance plan. Like after large storm events, the city, I mean, even forget storm events, just regular maintenance of the park itself, right? Like the city has a parks department. They've got maintenance crews that come out and just maintain the playground, the pick up trash, whatever. But then after they get a certain amount of rain, they come out and they do some cleanup around the perimeter of the wet pond, and just make sure that any trash that is captured by all of those plantings, that all gets picked up. Long-term maintenance of the bioretention and planters, that's another thing that they've got plans to bring vac trucks out there to clean out the planters, clean out the trash racks where the storm drain enters the pond. And then for the bioretention, similar, they have just like a periodic plan to send their crews out there a couple times a year to dredge it out. Same thing with the wet pond. There is, over time, there will be an accumulation of sediment in that pond, and so the operations and maintenance plan has the periodic time that they come out there to dredge it out and take that sediment away. You can kind of see on that walkway down there on the south end of the pond, we have kind of a little access ramp where they can like back trucks down there to do that maintenance.
Yeah. One of the questions here was how long did it take to secure all the necessary permits for this before you could even break ground? I imagine the permitting for something of this size and nature would take a pretty decent chunk of time.
Yeah, I don't know that I can speak to the permitting specifically, but it was so it was a construction manager at risk type project. So
Okay.
we did prepare the 100% plans and then kind of turn that over to the CMAR, and then they took it from there. But I think the entire process from the beginning of the design in earnest was 2017. Around 2017, 2018, we wrapped it up around like 2019, 2020. They started construction in 2020, finished in 2022.
Okay. Question here about the weir. Why have the weir and the extra expense of that wall? And why not just have it drain out of the pipes directly into the retaining wall?
So let me go back to that slide here. Might help me illustrate that a little bit better. So The reason for that, we wanted to have we wanted to be able to back up as much water as we could in that pond without overtopping. If we had placed, like if we had just simply elevated the holes in the retaining wall, like say we don't have the overflow weir and we just raised those outlets a couple of feet, which I assume is what that question asker is suggesting. We could have done that, but what that would have done is it would have required that we put more openings in the wall. We needed to have kind of that hard elevation where it's like above that elevation, all of a sudden lots of water can exit the pond at that elevation. If we had just kind of like put some openings in the wall, as soon as it reached that kind of lower elevation of one of those openings, you would have had a little bit of water spill out, and water would have had to go up a couple of feet higher to really start pushing flow out. By having this overflow weir, this 80-foot, that's also why it was so long, 80 feet long. As soon as you get a couple of inches of water over that, that's kind of a lot of flow that can leave over that, enter this little trench, and then get out. So it had to do with that kind of window of water surface elevation, and we wanted to keep that like really tight, if that makes sense.
Mm-hmm. Yeah. And I see that there's another kind of thread that I'm seeing in here when I was looking at this. Some more on kind of like the treatment elements involved. So
Mm-hmm.
there's one that says, are those pollutant removal rates from empirical data or theoretical? Is the bacteria being removed simply via filtration? And then they have that picture of the storm event. Looks like a lot of turbid water in the pond, and they assume that it's the
Mm-hmm.
Clay Hills in Atlanta. So what treatment removal processes were used to clarify runoff or remove suspended solids causing the turbidity? And then how is that water polished as well? So some questions there about, the treatment of the water
Mm-hmm.
after it's been captured and everything, kind of like the nature of that water. How is that then made more clean, essentially?
Yeah, so I guess the first part of that is it's not, to my knowledge, there hasn't been any like formal uh, empirical testing of the runoff. This is all kind of like theoretical based off of their criteria manual, and it's based on filtration, right? Like it's based on the fact that there is a certain volume of water that will enter the planters, that will enter the bioretention cells, and be filtered through that engineered soil before then entering the pond. Um, so yeah, to answer that first question, it is a theoretical,
Mhm.
calculated amount of water quality treatment. And then on the question
Yeah,
about, where is that slide?
yeah.
The
There's
question about
the
you can see that that water does not look very inviting
yeah.
from
I
the
don't
ground.
think the slide is moving for us. Hold on. Let me see if I
So
can
okay,
get it. Trying to find that one.
but yeah,
There, I think
the oh,
I think
there it
this
is.
is the one,
Slide.
right?
So yeah, this slide you can see here during a storm event. Yeah, very brown. I actually it rained when I went out there to visit it once, and it tends to look like this when it rains, and that's just because yeah, the upstream areas there's Atlanta has a lot of uh,
Mhm.
clay soil, and that's what ends up. That's the sediment that we're trying to capture and not move downstream if we can help it at all. And so, yeah, during a storm event, it absolutely looks like this. Even like a day or two after a storm event, it's going to look like that down in the wet pond. But then, as it has time, as that sediment has time to settle out, you get the water that looks kind of like not as brown, looks a little bit more blue and inviting. So it's that's part of it. Part of it is the sediment settling out over time, and then part of it is just some of that getting during smaller storm events. Not like a 50-year event like you saw in that picture, but if you just got half an inch of rain, that water should primarily be captured by the planters and the bioretention cells. And so in that case, you wouldn't even really be seeing that water reach the wet pond in the first place.
Yeah, yeah. Got a couple here on the soils too. There was how do you test infiltration rates in the engineered soils of the bioretention areas, and then what type of engineered soil was used? They mentioned that there's some recent research that's found that higher compost mixes can export phosphorus.
Yeah, I don't have that information like right handy right now, but there's a specification that the city has for their engineered soils, and I also don't know what sort of testing has been done to verify the infiltration rate, but the way that it's designed, it's not so much that we are assuming a certain infiltration rate, like, okay, this stormwater planter can infiltrate X inches per hour or per day or whatever into the stormwater planter. What we're assuming is that water enters the planter. So if there's a certain amount of runoff that enters that planter, it's going to fill up and it's going to reach that elevation that it's going to then kind of like overtop the concrete and go to the next stormwater planter and so forth. And so like our assumption is those will all fill up, and then like over time it will gradually infiltrate. But like we're treating each of these rain events as though it just produces a volume of water that reaches that. We didn't design it to infiltrate during the storm event. So I don't think the infiltration rate per se, if it was, an inch an hour or 0.2 inches an hour or something in between, like that's kind of immaterial to all of these numbers that I've been talking about in the rest of the presentation.
Yeah. There seem to be a couple of questions here too about mosquitoes, standing water and all that. Is that a consideration that you guys had made, and how did you address that if it was a consideration?
Yes. So the answer to that is that the pond is stocked with mosquito fish that will eat the larvae and kind of help keep that under control. So that's one way that the city's treating it, and I think it's working well. Anytime that I've been out there, there's not mosquitoes around, so must be working.
Your experience is working. So, and I apologize. There's still more questions here about the maintenance. I think everyone's, you look at how beautiful this whole thing is. I imagine a lot of folks are looking at this and being like, wow, how do you make sure it stays so beautiful? But so one was like, how do you maintain the lawn after a storm? Is there a sanitary concern for residents regarding that? Because they mentioned they had a similar scale project, and the county had raised concerns about the lawn's area's cleanliness after a storm, and just wondering how that's maintained compared to like the actual wells of water that are out there. So
That I am not as familiar with as far as like how they treat the lawn, but my understanding is they've got people out there all the time. It's pretty high profile project for the city, and so they have people out there, like I think on if not a daily basis, like certainly a weekly basis, to kind of make sure that things are cleaned up and looking good.
Yeah. You mentioned the high profile nature of it. There was a question in here too, just kind of about the local public. How much knowledge do they have of this park and kind of what it does? You mentioned like in the presentation, you mentioned those little standing posters essentially that people can look at and whatnot. Have there been other media efforts that the people have been made aware of this project in its very nature?
Um,
Like what's that? How does that look? Have you been a part of that?
I have personally not been a part of that, but I know like they may have. I don't know that they have any ongoing outreach efforts, kind of like aside from the signs that have been placed around the park. But during design and certainly during construction, there was a lot of public involvement, public meetings, Q&A from the public, making sure that like people understood what was being done and what purpose this project was intended to serve.
Yeah. All right. Well, we are at the bottom of the hour, so we're going to have to cut it a little bit short. I'm sorry that we started a little bit late. We had some technical things we were working through before starting, but we're going to have to close it out. We have a lot more questions still left here, so any of the questions that we didn't answer, we will get to offline. Thank you for your participation today, Garrett, and to everyone who was watching this as well. As a reminder, at the conclusion of this event, you'll receive an email with a link to download your certificate to use for Stormwater University credit or for one personal development hour for attending the webinar. That concludes the presentation. I'd like to once more thank Garrett for participating, and of course to all of you for joining. Don't miss our next session, Stormwater Management and Maintenance in a Changing Regulatory Landscape. You can join the session by exiting out of this event and going back into the agenda. Select the session by clicking on the View Session button to attend. So thank you all, and we'll see you in the next event.
All right. Thank you.